Good afternoon, everyone. My name's Howard Herzog. I'm the Executive Director of the MIT Energy Initiative's Low Carbon Center on carbon capture, utilization, and storage. And this afternoon, I'm happy to welcome Sarah Budini from Imperial College for her talk today. Sarah got her care as a chemical engineer, so it's appropriate we're here in the chemical engineering building. She got her undergraduate and master's degrees at the University of Genoa in Italy as part of her studies there. She also spent a year at the University College of London. When she graduated, she spent a couple years as an aerodynamic engineer in the power generation industry. From there, she went back to get her PhD at Imperial College, where she was a Marie Curie Early Stage Research Fellow. And upon graduation, she joined the Sustainable Gas Institute, also at Imperial College. I met Sarah a number of times over the past year or two at different meetings for carbon capture and storage around the world, and she's been presenting some major study they did on can technology unlock unburnable carbon. That's what she'll talk about today. So also talking to Sarah a little, and she told me that the president at Imperial College is Alice Gast, who used to be the VP of Research and Associate Provost here in the early 2000s. So there's lots of different connections. So without further ado, Sarah, I'll turn it over to you.
Thank you, Howard, for the introduction, and thank you everyone for being here tonight. I understand probably the weather outside is not very tempting, and I promise I didn't bring it from UK because it never rains like that badly. But anyway, so tonight I'm going to talk about this white paper. You can find some copies outside, and it's the second white paper that we have produced at the Sustainable Gas Institute. So I will start by giving you an introduction of what the Sustainable Gas Institute is. So basically, it's quite a new institute. It was founded in 2014, and it's an industrial academic collaboration between UK and Brazil. And it was initially established on the hub and spoke model with the hub in UK, in Imperial College London, and a number of spokes. At the moment, we have only one, the first one that was opened in December 2015, the Research Center for Gas Innovation at the University of São Paulo. So basically, the aim of the institute is to investigate the utilization of the decarbonization of the energy system with a focus on gas. And we are working on two main research activities, and I'm personally involved with both of them. So the first one is the production of white papers. So basically review papers on controversial topics, and like the one I'm presenting tonight. And the second activity is a new integrated assessment model called MUSE that will be hopefully launched later this year. So these are the three white papers. So the first one is on leakages from the gas supply chain. It was produced in 2015 from some colleagues of mine. Then I'm presenting today the second one, so can technology unlock unburnable carbon? And the third one will be launched in July on the future of gas networks. So this is the basically Sustainable Gas Institute. So you can see the management team on the top half of the slide, and then the research team. So as you can see, it's not only quite a new research institute, but it's also quite small. But we are hoping to expand it in the future. And we have also an international advisory board that is helping us in deciding, for example, what to explore next, both with the modeling activity and also with the white paper activity. You may be familiar with some of the faces on this slide. For example, Professor David Allen from the University of Texas at Austin, or Dr. David Daniels, who is the Chief Energy Modeler at the EIA, who is helping us especially with the development of MUSE, the Integrated Assessment Model. So going back to the topic of the white paper, can technology unlock unburnable carbon? So definitely COP21 and more recently COP22 were very important reminder that we have carbon constraints. So that basically means that we have a certain amount of carbon dioxide that we can release into the atmosphere if we want to stay below a certain climate target. And this climate target was expressed in some specific terms in COP21, where people have mentioned that we would like to investigate the possibility to stay well below 2 degrees. And definitely there is an emerging literature that's investigating the decarbonization of the energy system. And the research question that we had was if we can access energy resources, specifically fossil fuel resources, while meeting this climate target. So more specifically, when we mention technology, what we mean is mainly carbon capture and storage. And this paper has quantified the impact of using CCS worldwide on the utilization of fossil fuels. So in the white paper, I've reported different climate target scenarios, but in the presentation, I'm only reporting the 2-degree climate target. So the methodology that we have adopted consists of first a systematic review of academic, industrial, and grey literature. And the methodology was initially proposed by the UK Energy Research Centre and was adopted by us and also modified in order to perform this work. And you can see the main steps of the methodology here. And basically, the idea is to use well-defined search procedures in order to be clear, transparent. For example, we had in the scoping note a list of all the databases that we have analyzed and all the keywords and each search, like how many items we have found in specific databases. And also, we have appointed an expert advisory group that has helped define the scoping note initially, and then who has reviewed the report before its launch. And then the second part of the methodology is the analysis of energy scenarios. So I'm going to explain later which databases we have selected and which scenarios we have used in order to quantify the role of CCS in the utilization of fossil fuels. So basically we have compared scenarios with CCS against a scenario without CCS, so without carbon capture and storage. And also we have performed some research using the TM-Grantham model. So basically in the next 50 minutes, I'm going to start by talking a little bit about the carbon budget and what we mean with the term unburnable carbon. And then I'm giving a brief overview on carbon capture and storage for those of you who are not familiar with this technology. I mean, I suppose most of you are, but just in case. So a brief overview, a list of potential barriers that we have also presented in the white paper, and then the current status of CCS. And then I'm going to present what we have found in the literature about the role of CCS up to 2050 and what we have done to analyze its role up to 2100. So the database we have selected, the scenarios we have compared, and also why a capture rate is a key parameter for this analysis. And then I'm going to conclude. So if we talk about carbon budget and unburnable carbon, for example, we can use this figure, which is figure 1 not only in the presentation, but also in the report, where you can see a number of sources and the estimation of the carbon reserve. So basically, this is the estimation of the fossil fuel reserve expressed in gigaton of CO2. And the dark section is representing the unburnable carbon, so the part of reserves that we should not use in order to meet the climate target of 2 degrees. And the top part is the burnable carbon. So basically, the burnable carbon is equivalent to the fraction of fossil fuel reserves that we should be able to use while meeting the climate target. As you can see, different sources are reporting different numbers. There is a lot of uncertainties. Uncertainties in the estimation of the fossil fuel reserves, uncertainty, for example, on the on the climate target itself. And also different sources have used, for example, different time frames, different models. More or less, we can say that this carbon budget, which is equivalent to the burnable carbon, is more or less around 1,000 gigaton of CO2. So if we now move to carbon capture and storage, as I said, I suppose most of you are familiar with it, but just to briefly describe it, it's a technology that aims at separating, transporting, and storing carbon dioxide underground. And there are three main capture technologies: post-combustion, pre-combustion, and oxy-combustion, and a number of separation technologies. And the picture I'm reporting here is from the chemical engineering department of Imperial College. We are very lucky. We have a CCS pilot plant that covers, I think, 4 floors of the central part of one of the buildings of the chemical engineering department, and is mainly used for educational purposes, so with the undergraduate students. But we are also start thinking how to use it for doing research, for example, to test new sensors like wireless sensor, for example. So this is just an example of a post-combustion, CCS with power generation, and we have a power plant, then the capture step, and then the transport, compression, transport, and storage part. So as engineers, we are mainly familiar with most of these steps when they are on their own. So the challenge seems to be mainly to how to integrate all of them and how to integrate the system, so the process plant with CCS. So there are definitely a number of potential barriers to CCS. We have called them potential because if you read the white paper, you will see that some of them, they are not really barriers. And for the sake of time, this is a full list that we have reported, but for the sake of time, I'm going to talk about the cost of CCS and the geostorage capacity, so you can see what I mean with potential barrier. So the slide, I don't know if you can read it, but basically it's reporting the cost of the avoided CO2, so the cost of avoiding the emission of 1 ton of CO2 in US dollars. So basically this cost includes capture, transport, and storage. And as you can see, we have reported also the minimum and maximum values that we have found in the literature. And there is definitely a wide range. And this range depends on the process plant and their analysis on the type of capture technologies and also on the type of storage sites. And according to the literature review that we have performed, the highest value for the cost of avoided CO2 is $160 per ton of CO2. The second potential barrier is the geostorage capacity. So the question is, do we have enough space to store underground CO2? And here we have reported the estimates of the total and also regional global CO2 storage capacity. So the total estimate is the full bar, and then you can see the red line that is basically representing the depleted oil and gas fields. And what you can, I hope you can see the map on behind the bars. So, but anyway, you can read also text, and there is quite some space, storage space in, for example, North and Central America, in South America, and also in Asia. But even also in this case, the uncertainty on the estimate is quite wide. So we have estimates that go between around 10,000 and 33,000 gigaton of CO2 of storage capacity. So this is an example of a potential barrier, because it's something that before performing this analysis, we weren't sure what the answer was, like, do we have enough space? And after performing this review, even the lower estimate on a global level is enough for storing CO2 with CCS. So this is, on a global level again, is not a barrier anymore. At the same time, we are aware that certain countries may have issues with their own geology, and so they may not have enough space. So, for example, one case is Japan. But again, on the global level, the capacity is enough. So this graph is representing the current state of CCS. Actually, the bar, the global figure should represent also 2015, but we had very nice designers who did all these figures, and so we weren't really able to, change the figure without the designers. But anyway, what you see is basically the total number of CCS projects, so the total bars, and in dark blue, the number of projects in operation. So again, there are quite few projects around United States, but also Europe. And if we look at the total trends, what you see is that the total number of projects is decreasing over time, while the total number of projects in operation is increasing over time. And again, I've not reported the numbers for 2015, but the trends is the same. So our basically comment on this trend is basically that previous investments in CCS have now resulted into operating plants, but there haven't been many recent investments, so new projects that were at the very early stage have been basically canceled. So when we are looking at the potential role of CCS in the field of fossil fuel utilization, we found a paper that was covering up to the year 2050. And this paper was published in Nature, and the authors are from the University College London, so McGlade and Eakins. The topic of the paper was not unburnable carbon, but anyway, the numbers reported were very useful for our purposes. So if we focus on the total value, what you can see here is basically the burnable fraction of the fossil fuel reserves with CCS and without CCS. So of course, as you would expect, you can access more fossil fuels if you're adopting CCS worldwide. So even the authors themselves say that the CCS has the largest effect on the single largest effect on the results, but the impact is not that important. So it's 5.5%. That means basically you can access 5.5% more fossil fuels while meeting climate target with CCS than without CCS. So what we wanted to do, starting from basically this paper, was to go beyond and see what was the effect up to the end of the century. And this is what we have done. So we have decided to analyze a specific database, so the IPCC Fifth Assessment Report database, and a specific project, so the EMF 27 project, that includes 18 integrated assessment models and a number of scenarios. For example, technology scenarios, the full technology portfolio scenario that includes all the technologies, so traditional fossil fuel, renewable energy sources, nuclear, CCS. The conventional portfolio that has a similar technological representation, but is a bit more limited on the renewable side, so it's relying more on conventional solutions. And the no CCS scenario where CCS never becomes available. And then there are different climate change scenarios. In the presentation, I'm reporting only the 450 ppm that correspond to the 2 degree. But in the paper, you can find also the 550 ppm scenario. And in the EMF 27 project, there were 2 time frames, but we have only looked at the models that were covering up to the end of the century. So this is the first conclusion from the work. So it's basically representing over time from 2005 up to 2100, the fossil fuel use in exajoule per year for the 3 scenarios. So the green one is the full tech, the dark blue is the conventional, and the orange is the no CCS. So what you can understand from this graph, there are basically 2 important messages. The first is that in all the scenarios, the fossil fuel consumption is peaking at a certain point in time and then it's decreasing over time. So they all see a decrease in the use of fossil fuel. And this is total fossil fuels, by the way. And the second message is that there are some differences between the conventional scenario and the full tech scenario. but the use of fossil fuel in the orange, so in the no CCS scenario, is very low by the end of the century. So there is definitely quite a difference between these two scenarios and the one that doesn't have CCS. And also, you cannot see it from here because I'm reporting the average of the outcomes of these 18 models minus those that didn't cover up to 2100. But you can see like how basically the error bars for the results. Of course, the uncertainties is greater towards the second half of the century. And another thing that you cannot see is that some models were not able to produce any outcome if CCS was not available. So basically, they considered that type of scenario infeasible. So it was basically impossible to meet the climate target without CCS. So what we have done, we have decided to compare the scenarios that for us is the best, so it's the full tech, against the one without CCS, so the green against the orange. And here we have reported the cumulative values of reserves expressed in gigaton of CO2, so this is the total reserves, and then how much you can access up to 2050 with CCS, while again meeting the climate target of 2 degrees, and how much you can access without CCS. And this number is basically what, according to McGlade and Ickes, was 5%. And we have seen a difference of 11%, and this is the average of like 14 models. So given the differences that there are among all these models, we think these numbers can be considered in line. But what was more interesting was to look at the full century. So the second two bars are representing the time frame from 2005 to 2100. And as you can see here, the difference is 32% between the amount of fossil fuels that you can access with CCS against the one you can access without CCS. And finally, I mentioned before that capture rate is an important parameter. So capture rate is basically representing how much CO2 is ultimately stored underground. And in most of the models that we have analyzed, this number is around 90%. Let's say between, I don't know, 85, 82 to 90%. And what we have decided to do was to use the TM Grantham model and to run a small initial study, a kind of sensitivity study on the how much the capture rate would affect the results that we reported here. So the graph is a bit complicated, but bear with me, I'm sure we can go through it together. So here we are reporting the capture rate from 64 to, I don't know, probably 96%. And here we are reporting the gas utilization in exajoule per year. And then we have three kind of screenshots. So 2050 in light gray, 2080 in light blue, and then 2100 in dark blue. So, for example, if you look at the specific capture rate, I don't know, 79%, then we see that the use of gas in 2050 is higher than in 2080 and is higher than in 2100. So this is similar to what we have seen before. So the use of fossil fuel, well, in this case, gas is decreasing over time. Instead, if we focus on a specific screenshot, for example, 2080, we see that higher is the capture rate. So if we move on this side, higher is the amount of gas that you can access. So in a way, these results make sense because the capture rate is representing how well CCS is performing. And the better it's performing, the lower are the residual emissions, and the I don't know, the stronger is the impact, let's say, of this technology. So in conclusion, we think that CCS can underpin the use of fossil fuel without endangering climate change, and we have seen through the presentation why we think this contribution can be estimated to 32%. And also the potential role is greater in the second half of the century. So you have seen how much the numbers have changed when we have looked only up to 2050 and then up to 2100. And then capture rate is a crucial factor, and it would be interesting to see if it's possible to go above 90%. There are some papers that for very specific case studies analyze how much the cost would increase with increasing capture rate. But there are just a few, and it would be interesting to investigate this topic more, and this is what we are doing at the moment also at the Sustainable Gas Institute. And then we also think that the cost of CCS is a short-term barrier, and I didn't have time in this presentation to justify this assumption, but if you look in the paper, you can see that we have reported the cost of carbon for these scenarios, and the projected cost of carbon are much higher than the cost of CCS, so it should overall be a short-term barrier. So just to conclude, I would like to acknowledge the co-authors of this work, Samuel Craver, Niall McDowell, Nigel Brandom, and Adam Hawkes, and also the expert advisory group, and especially Tim Dixon from the IEA-GAG, Nick Steele from Shell, and Christoph McGlade from the IEA, the International Energy Agency. And part of the paper was developed in collaboration with the IEA-GAG, and of course the opinion are the opinions of the authors only. So again, as I said before, there are some paper copies, but you can find these white papers and also the first one, and after July, the third one on our website. So you can just Google either the title or just use this link if you want to download the paper or if you want to download the summary. So thank you for your attention. Yeah, I think you have to just wait for the microphone. Someone is bringing a microphone. That guy there.
Thank you for your talk. Some chemical engineers are studying about the co-production using the CO2 as a reactant to produce some methanol or other fuels or chemicals. How do you think about these kind of production from captured CO2?
Do you mean what's my opinion?
Yeah. In the future, is it the useful strategy to produce chemicals, or it's better to produce methanol or something from fossil fuels as we do now?
Well, this is a bit outside the scope of the analysis, but in general, I think, and Howard, correct me if I'm wrong, but when we discuss about CO2 utilization, it can have a role, but when you look at the global numbers, like the problem is so big that it's something similar to when you talk about, for example, negative emission technologies. So they have a role, but they cannot make it on their own. And that's my opinion also on CO2 utilization. So you can go forward with that, but you cannot pretend like to solve this problem of CO2 emission only by means of CO2 utilization.
Thank you.
Why do you believe it is that the number of pilot projects has been decreasing? I would have guessed it was because people don't see it as economically feasible anymore.
Well, in a way, at the moment, CCS, unless you're talking about enhanced gas recovery or enhanced oil recovery, is never economically feasible unless you have an incentive for doing it. A plant with CCS will be always more expensive than the same plant with CCS, without CCS. So, I don't know, some oil and gas companies are asking for a carbon price in order to basically push the market and make it economically more feasible. But it's not really about, from a technological perspective, we know that CCS has a cost. And I think he has a kind of special role, because usually when you look at technologies that are very expensive, they are expensive because they are new. Well, in case of CCS, at the moment, I know there are many people working especially on the reduction of the cost of the separation step, but it's something that has been done when it was economically feasible. It has been done for years, like separation of CO2 for recovering oil, for example. So it's more a matter of, I don't know, it's more a policy problem than an ecological problem. You need like either an incentive or a carbon price. We have the emission trading scheme in Europe, and I mean the carbon price currently is so low that you can just pay basically whatever you have to pay, and it doesn't seem to be doing much at the moment. So.
So on this subject of the cost, though, do you have any kind of even rough estimate of what the cost per unit of energy would be with carbon capture and storage as compared to without? Or is it, is it 50% greater? Is it double?
In the paper, we have reported energy and efficiency penalty. The problem with cost estimates is that, well, it's more of a problem as a matter of fact. Most of the estimates are on, for example, on power generation. So when you look at costs of CCS in industry, that is something that for us is very important because, well, for me it's very important, sorry, because I am working on the development of the industrial sector for the Muse model, and we want to basically model certain technologies in industries and the possibility to invest in those technologies either with or without CCS. And we don't have, there are not many reports where you can find estimates of cost, or there are, but they are very specific, so they cover only one specific technology. That makes sense because when you run a case study, you need to specify everything, right? But at the same time, for us, that because we are at the early stage of development of this model, we would like, I don't know, maybe it's a bit idealistic, we would like to be able to somehow generalize a little bit more. But yeah, and when you have seen it in the map before, there are currently 15 large-scale CCS plants, so definitely there are not historical trends on the costs of these plants. What we found is mainly in the academic literature or some reports.
So I have a question. You talk about we should have enough storage space for CO2, but I think the storage space may have its own distribution. So in your analysis, have you considered that the carbon emission along with the distribution, like from your CCS plant to the storage place?
Are you talking about leakages or?
Not leakages, but transportation from your capture place to the storage place.
Okay, so for transportation, well, what we have seen is that basically, first of all, you could, in theory, transport CO2 in different ways, but it would be done probably via pipelines. And a problem, I mean, there are a number of problems. One problem is that where do you put this storage site? And that's more of a kind of public acceptance problem, because storage sites onshore are not really liked by the public. And so instead, if you are, for example, considering storage sites offshore, you have to look at the location of the emission points. If it's a power generation station, is it close to the coast? Is it not? How long should this pipeline be? If it's a small source, then can you collect the emission from different points, like a kind of industrial hub? And again, when you build a pipeline, where are you going to build this pipeline? Who is paying for the cost of the pipeline? If you're sharing a pipeline in a hub, if the pipeline is already there, maybe, I don't know, it would be easier as a starting point. So But I mean, there are so many problems.
So does that mean, like in your analysis, the cost of the distribution is not considered?
Now, the cost, it is considered. So there is also a table that you can find where we have reported the cost of transporting depending on the capacity of the pipeline and the length of the pipeline, and if it's onshore or offshore. So it is considered, but as in most studies, you will find that most of the cost is in the capture step, and then the cost of the pipeline, I mean, you can have a capital cost, so building a new pipeline, then there should be some kind of maintenance cost, but I mean, its contribution to the overall cost is minor compared to the cost of capture. So if you're interested in this topic, you can see in the report we have broken down like capture, transport, and storage costs, and then reported the overall, that is basically the avoided cost, the one I've shown before in the slides.
Thank you.
Yeah, over here. Hi. Hello. It seems like an alternative, an equivalent title to your paper would be, what is the future role for fossil fuels if there is no CCS and there's a restrained carbon budget? And the answer to that question would be, it's a pretty small future for fossil fuels. So if that's one of the answers from this paper, how are the fossil fuel community and the interests and advocates for fossil fuels taking the results of this report? What are their conclusions? Is there a lot of push that is coming from this work to advance or do more work on CCS to improve its economics, so that the path using CCS is more likely to occur?
Actually, we would have expected more feedback from the oil and gas industry, because when we talk to people who are more, how can I say, concerned about the environmental aspects, they used to tell us that we want to use more fossil fuels. You know, I mean, even Greenpeace is against CCS because they say that, I don't know exactly what they say, but I suppose the idea is that if you have CCS, then you keep using fossil fuels instead of investing in, for example, renewables.
I think their worry is, I think Greenpeace and other environmentalists' worry is that there's no way of guaranteeing that the carbon will remain sequestered, that there could be leaks in the storage fields. That's one of their concerns for sure.
And I understand the concerns because, as I mentioned before, we have experience in separating CO2, transporting, injecting, but we have never tried to keep it underground for like, I don't know, forever in theory, or I don't know how long. And we should have a monitoring system in place, and then that's definitely where the part that would be in a way more, I don't know, experimental. We didn't get much feedback, honestly, from the oil and gas company. I have to say, for honesty, I don't know, is that we are funded by Shell. And actually, we were initially funded by Imperial College and BG, and then BG was bought by Shell. Usually when we interact with our funder is when we decide which topic to investigate. But I mean, as I said before, the methodology that we have used is completely transparent, so you can just repeat the analysis. So I think it's showing that the oil and gas industry is exploring the idea as an alternative. And actually, the idea of unburnable carbon started as, it was called like carbon bubble. So a kind of, should we divest away from oil and gas because oil and gas companies have access to reservoirs that they may not be able to use. But our background is strongly in scientific and engineering, not really in finance. So we have decided to look at the problem for a more engineering perspective. I don't know, I think there is an opportunity there for them, but it's not I mean, it's up to the oil and gas companies, really.
So I would just make... Thank you. Just make a comment to follow on what you just were addressing. Speaking about these things in terms of the carbon reserves is always a little bit of a tricky thing because they're not all the same, the carbon reserves. So I think most of what you have there about reserves that might be unlocked is really coal reserves. So the oil companies, it's not going to change very much what reserves they utilize, except at the farthest reaches of things. The incentives, I'm not sure. There's a lot of conversation about stranded assets, but it's not very well informed about whether it really financially affects who in what ways. There are enormous coal reserves that wouldn't be utilized for the longest time. They're stranded anyway. So I just think that that's trying to figure out about people's incentives from the reserves that are stranded is, it always gets people twisted up, and it's not a very accurate representation of the financial interests of the parties at hand.
So I have two comments on what you just said. The first one is that the reserves that we have reported in the paper are the 2P, so the estimate for the think it's possible and probable, the 2P, and it's a current lower estimate of reserves. The second point is that you're right, it depends on exactly which fossil fuel you are talking about. Oil is usually more utilized for transportation, so it's a sector where you cannot really use CCS. And between gas and coal, yes, definitely, it would be more beneficial for the coal industries to use CCS. But again, I don't know, we have reported I know it's an opportunity, and I understand if you can choose and your business is going well and you don't have an incentive for doing CCS, then you don't do it. But at the same time, if like the market is shifting somewhere else away from coal, then it could be again an opportunity for them. But
Hi, thank you. I was just curious, two questions. In terms of the geological storage, the numbers that you were showing, what was the split roughly between onshore and offshore with those? And then second follow-up question, has there ever been a pilot project for storing CO2 offshore? I'm aware of ones onshore, but are there any offshore so far?
the split, I'm not really sure, so I cannot really answer the question. But if you look at the paper, we have the full list of references, and they may mention like which storage sites were onshore and offshore. Again, for the pilot plant, maybe even large scale. If you look into the Global CCS Association, you can download a table with all the CCS projects in all the phases, from the initial conceptual to the operating phase, and then you can filter the result and see the type of storage site that you're using. And I'm not sure, I don't want to say something like that is wrong, but I wouldn't see why there isn't anything offshore, especially because, like, I don't know, there are towards depletion oil and gas fields offshore. So these are, and the pipelines in those cases are already in place, and for some reservoirs, they are already doing a nice oil recovery. So, I mean, a further step could bring it towards, I don't know, making it permanent storage. But yeah, storage is not really my field, so I leave you to the reference list. I think here, yeah.
So your study basically took a 2 degree C scenario, and it looks more and more like that scenario is anywhere between implausible to impossible, especially on the path we're on now. And so two questions. One, in some of the models to meet these 2 degree C scenarios, was negative emissions used in some of these models, and to what extent? And secondly, in your study, did you look at other emission scenarios such as a 3 degree stabilization or even higher?
So the two climate scenarios that we have analyzed were the 2 degree, so the 450 ppm, and then the 550 ppm, because those two are the ones you can find in the FIFA assessment report database. And this 550 ppm corresponds to, I don't know, a bit above 2 degree, but depending on the likelihood of meeting that climate target. I think this is like this is kind of the continuation of the conversation we already had. Like, okay, we should be going in that direction, but it's not really happening. But we really would like to go in the direction. And I don't know. I mean, the IPCC has a special report coming probably next year on how to meet the 1.5 degree target. So I'm sure it will be very interesting to to read that report and see what they say about it. Also, the International Energy Agency is working on how to meet this climate target. I mean, from an integrated assessment modeling perspective, I mean, a model is just a model. You can force it to do it. What you want it to do is just a mathematical model, you know. But then when you project, when you see like that the trends have been a certain type, and then in order to meet that climate target, there is basically a peak, a point in time where you should change completely. I don't know, I think it's already say everything, at least to people who understand, who are able to read this graph. So I don't know, hopefully we will, I don't know, slow down with the emissions. But I mean, there are so many, it's a very difficult topic that involves so much more than just technology and engineering. I mean, engineering, technology, and science, you know, are easy. Well, yeah, numbers are easier than people usually, so I don't know.
So as you mentioned, in your models, you didn't include any carbon tax or any carbon prices. Is that correct?
Well,
We're
first
calculating
of all, yeah, it's not our model, so those models come from the FIFA assessment report. And my understanding of those models is that they had to meet the climate targets. So that's the way they run, basically. They had to meet the climate target, first of all, and then it depends on the models. Some models are simulation-based, others are optimization-based. So some models were optimizing like were performing a cost optimization, but that was the most important constraint was the climate target.
Okay, so I guess there had to be a carbon price, because I know in the IEA Times model, I guess it's similar to these models, but they also kind of have different carbon prices or carbon taxes depending on each scenario, 2 degree scenario or 4 degree, or so. Okay.
Yeah, I mean, actually, the carbon price is quite interesting from, again, an integrated assessment modeling perspective, because you can run different simulation and see at which carbon price the model is switching from one technology that is probably cheaper and is performing a little bit worse, so it's consuming more and emitting more, towards something that is maybe new, so more expensive, but better performing, so has lower emissions.
The range of carbon costs for different scenarios is very wide, from, I think in one case, $10 per ton of CO2 to $160 per ton of CO2. Is there a way to narrow down this range in order that better policy decisions can be made?
So for example, what we have done was to aggregate certain results in order to represent, for example, a certain, I don't know, industrial sector. But then you can basically look into the sector and say, okay, we are talking about, I don't know, emission from the iron and steel industry. But then which type of CCS are you considering? Are you considering post-combustion, pre-combustion? Which type of storage sites? So basically you could disaggregate all the numbers and report all the case studies. The problem is that certain case studies were for specific, I don't know, combination of process plant and CCS solution were not performed. And again, these numbers come from the literature. So it's also very difficult. We were also thinking, okay, maybe we could look at the distribution of costs, you know, where you have a minimum and a maximum, but then the average would be very difficult because it would depend more on the number of papers that have reported the numbers rather than if the numbers is the real cost for that specific case study. I don't know if it makes sense. But anyway, going back to your question, we should basically disaggregate all the costs. And then for a specific combination of power plant or process plant plus CCS solution, then you could see what would be the specific cost. Does it answer your question?
Yes.
Okay.
Thank you. Given the fact that the 2-degree scenario is so difficult to achieve, I mean, you mentioned it yourself, isn't it dangerous to conclude that with CCS we can burn more carbon?
Why do you say it's dangerous?
Well, because to get to these 2-degree targets that these integrated assessment models show, you need a whole wide array of different technologies, very high penetration of renewable energy sources. And CCS, I think, is a very important part of that. But isn't it, to get to this 2-degree target, we should just leave the carbon into the ground, use CCS to, well, the assets that are already there, or apply them to biomass, for example, and also kind of invest in these other renewable energy sources? Isn't this kind of giving a license to operate for fossil fuel companies?
Well, consider that these models, they start from the current installed capacity. And from where we are now, they show different possible pathways where you basically, for example, have to limit the penetration of new technologies, because it wouldn't be realistic to think that you can switch from fossil fuel to renewables in, I don't know, 5 years worldwide. So they are starting from the current situation that is heavily reliant on fossil fuels, and then showing, while the use of fossil fuel is still decreasing, because that's a trend that we should see, hopefully, then they are showing how we can meet the climate target. And I would say it's rather the opposite. So these models are showing first that none of the currently available and commercially available technologies is the best one and the only one that we can use, and then it would solve all the problems we have. And at the same time, those models that were not able to find a solution without CCS are basically reinforcing the same concept. So we need, and I mean, that's the name of the scenario itself, is the full portfolio, because I think nothing is, we need like a full portfolio of technology. And the last comment on this point is that when we talk about CCS, most of the studies, for example, on cost are on power generation, and then you start to associate CCS with power generation. And with power generation, you can do it through renewables, okay? But then what do you do with industrial processes that, for example, I don't know, the cement production where you still emit carbon dioxide? There isn't a way to, unless you switch process or change materials that, I mean, is not very easy to do, there isn't a way to reduce the carbon emission from processes, not from fossil fuel combustion. So there is definitely where, I don't know, CCS at the moment couldn't be replaced with any other technologies. Well, for power generation, yeah, you can say, okay, we can have more renewables, for example. But again, you need to look at how the current situation could evolve over time.
I think we're going to have to stop there. So once again, let's thank Sarah for a very interesting
you.
talk and discussion.
Thanks.
And if you have some more questions, she'll be available if you want to come up and ask any more. Thank you.